Oxidation-reduction reactions are another type of reaction, and these involve the transfer of electrons. So they're called oxidation-reduction reactions, or redox for short, not redox. And that it actually looks a lot like red box without the B, but it's redox. I guess because oxred sounded dumb. Reduction oxidation sounds dumb too. I don't know. So oxidation reduction or redox. So those are the two names we use. Redox, yeah. Redox reactions are responsible for a lot of things that we observe in everyday life. Iron rusting is a redox reaction. If you get your hair bleached, that involves a redox reaction. Production of electricity in batteries, and who doesn't use batteries, right? I think most of us have a battery in our pocket, right? That is involving oxidation-reduction reactions. A lot of these involve the reaction of a substance with oxygen, but not all of them do. So here are some examples. The top one is the equation describing what happens when iron rusts. We get iron metal, which is a solid, reacting with oxygen gas, and it forms iron 3 oxide, which is rust. Rust is a solid, but it doesn't have the same physical strength that iron does. And so, you know, your car rusts. You guys are spoiled out here. I grew up in Iowa and Minnesota, where they put salt on the roads, and that's where the term rust bucket came from, because the cars just like disintegrate before your eyes. Question?
How do they neutralize it?
How do you neutralize rust? Well, you can't reverse the reaction and get back the solid metal that you have. You can prevent the rust. Once it started rusting, there are things that you can do to stop it from rusting more, and most of that involves eliminating the oxygen. So,
well, for like a car, you have a rusty car and it has rust on it. I know they have a chemical that you can put on it, basically, that prevents that amount of rust, the continuation of rust.
Yeah, you can stop it from rusting more, but you can't undo the rust that's already happened. And that probably it involves eliminating the oxygen. Like, you know, if you take like your outdoor patio furniture, you know, wrought iron, it's iron, and it'll rust if you leave it out in the backyard. If you spray it with Rust-Oleum paint, that paint will form a coating on the iron that will prevent the oxygen from getting to the iron, and so then it can't rust. And so, like, you know, we used to undercoat our cars, and they put this thick layer of stuff on the undercarriage of your car that will prevent, and water accelerates the rusting process. It kind of facilitates it. It doesn't, it's the oxygen that's causing the rust, but the water helps it to go. Well, if you just had hydrogen there, it wouldn't actually react with the oxygen unless you had some sort of a spark, and then you'd have a little more reaction than you wanted.
And why don't they have more? They have less rusting in like drier climates. Right?
In what?
In drier climates, no doesn't rust nearly as fast. Or
Yeah.
Really all,
Well, part of it is, I mean, like here in the Central Valley, it's a drier climate, but it's also a warmer climate, and so they don't use salt on the roads. Up in the mountains, they don't even use salt, they use sand. The salt that gets on the cars in the winter, it makes the rusting happen much faster. It allows the transfer of electrons. The salt and the water allow the electrons to transfer between the iron and the oxygen much faster. So if you had just iron and just oxygen and no water or anything else, I'm pretty sure that nothing would happen. But when you have these other factors which sort of act as a catalyst for that reaction, then the rusting occurs. Yes?
Like having the salt would act as an ionic compound and therefore allow the transfer.
Right, because salt is an electrolyte, and it allows the transfer of electrons. And in your battery, your car battery, even in the sealed ones, there's liquid in there. There's a salt solution that allows the electrons to move and be transferred from the one type of metal to the other type of metal. There's all different kinds, like a nickel-cadmium battery. You have electrons moving, I forget which way it is, from the nickel to the cadmium or the other way around. They want to go in that one direction. And you will allow them to do that by having this a substance that will conduct the electrons. So basically, when you get, especially with salty water on iron, it essentially is setting up a battery that is just discharging constantly, and it just eats up your metal. Yes?
I'm just confused. Is it the O2 in the air, or is it the oxygen in H2O that's reacting?
It's oxygen in anything. It's not oxygen that... Water generally has some oxygen dissolved in it. It's not the oxygen bonded to the hydrogen in the water molecule itself that it's reacting with. It's oxygen either dissolved in the water or in the air.
Okay.
Yeah. So, understanding the chemistry that's going on has allowed people to find ways to prevent this thing from happening. And, we have other sorts of oxidation-reduction reactions where you can electroplate things onto other substances, and they do that in making computer chips and all kinds of stuff. And so you can put metal where you want it to go, where it would be impossible for you to physically cut strips and put on there. It's really pretty cool. So there's a whole field involving oxidation-reduction reactions with metals. It's pretty cool. So that's an example of an oxidation-reduction reaction that we're probably all too familiar with. And here's another one, and this is combustion. So combustion reactions are also oxidation-reduction reactions. So here's methane, which is in natural gas, and that reacts with oxygen and forms carbon dioxide and water. So combustion of natural gas is an oxidation-reduction reaction. Now, if you turn on the burner on your stove and let natural gas escape, it's mixing with the oxygen in the air, but does it combust? No, you have to get it started, right? There needs to be a spark. Once the spark starts the reaction, it generates enough energy that it keeps itself going and gives off lots of heat. And it's a little bit like the rust thing. If there isn't the right combination of things to start the process, then it won't happen. And water helps make it happen, especially salty water. So we need to understand what oxidation and reduction mean. The fundamental definition of oxidation is the loss of electrons. And reduction is the opposite. Reduction is the gain of electrons. And so, yeah, good luck remembering those, right? It's another one of those, this thing is one and the other is the opposite, but how do we remember them? So we have a mnemonic, oil rig. Oxidation is loss of electrons, OIL. Reduction is gain of electrons, oil rig. Oxidation is loss, reduction is gain. And even when you've been doing chemistry for a long time, you still say that in your head, because that's how you remember it. So if there's going to be a loss of electrons, there must be a gain of electrons, because electrons do not disappear. Electrons can be transferred from one substance to another, but they don't disappear. They also don't come out of nowhere. So you can't have one substance being oxidized. Oxidation is loss of electrons. It's losing electrons. Those electrons have to go to something, which means that something else is gaining electrons and undergoing reduction.
So it's a simultaneous reaction.
It's a simultaneous thing. It's, okay, if I'm losing, then you're gaining. If you're losing, then I'm gaining. It's just a question of which direction it's going in. What you need to know for now is how to identify an oxidation-reduction reaction or a redox reaction. So here are the guidelines that the book gives you. If you have a substance reacting with elemental oxygen, that's O2, like that methane combustion reaction, CH4 plus O2. Anything plus O2 is most likely going to be an oxidation-reduction reaction. If you have a metal reacting with a nonmetal, it's going to be an oxidation-reduction reaction. Because what kinds of compounds do metals and nonmetals form when they get together? Ionic. In ionic compounds, you have ions. If you have a metal that has no charge becoming a cation, what happened to it? It lost electrons. It was oxidized. And the nonmetal was neutral, and now it's got a negative charge. It gained electrons. So if you've got like sodium and chlorine reacting to form sodium chloride, that's an oxidation-reduction reaction. So more generally, if you have one substance transferring electrons to another, that's an oxidation-reduction reaction. So you may be figuring out that some reactions can be classified as multiple types. It could be a neutralization reaction and a gas evolution reaction. Okay? So this is the sort of thing you need to be able to do. Which of these are redox reactions? So let's look at A. Is that a redox reaction? Well, what were the guidelines we had?
No.
Metals reacting with nonmetals. Lithium and chlorine, is that a metal reacting with a nonmetal? Yep. That's an oxidation reduction or a redox reaction. So that's a redox. How about the second one? 2 aluminum atoms reacting with 3 tin ions to form 2 aluminum ions and 3 tin atoms.
No. No.
Well, we got to think about this. How did Al become Al3+?
It gained, it lost oxygen.
It lost electrons.
yes.
So yes, that's an oxidation-reduction reaction. And the tin gained electrons to go from 2+ to 0. That's a redox reaction. So C, lead nitrate plus lithium chloride giving us lead chloride and lithium nitrate. Is that a redox reaction? Why? Well, what do we have here? This is Pb, 2+, and this is NO3-, and this is Li+, and Cl-, right? Those are 2 ionic compounds. And over here, we've got Pb, 2+, and Cl-, and Li+, and NO3-. Anybody gain electrons or lose electrons? No. Tricked you.
I have a question about B.
Yes.
When 10 lost 2 electrons,
Mm-hmm.
and then Al gained 3, how did it gain 3 if 10 only lost 2?
Well, there were 3 of them.
Okay.
So between the 3 tin ions, they lost a total of 6 electrons. And between the 2 aluminum atoms, they gained a total. Yeah.
So if charges are changing, that means it's,
Right.
so that's the key, is the charges.
So for B, the key there is to see that the charge changed on those ions.
And for C, the charges didn't change. But
Right.
Although the change of transfers ions and things are sharing electrons.
The ions swapped partners. It's a precipitation reaction. We did have a chemical change there, but there wasn't a transfer of ions involved. A transfer of electrons. They just swap partners. But each ion is the same. They didn't become a different ion. How about letter C? Now you're really spooked and you don't know what to answer.
Because they're not, are they both negative charges to start off with?
What was the first guideline for reaction with elemental oxygen? So carbon reacting with elemental oxygen, this is going to be a redox reaction. Isn't this fun?
But they're not exchanging anything.
Carbon has a charge though.
Well,
They're
no.
just covalent, they're just sharing.
See, there's no ionic compounds involved here, and I don't think we talk about this in 3A. There's something called oxidation states, which is a way of just keeping track of charges that aren't really charges. And if we follow the oxidation number rules, then we see that, yeah, the carbon and the oxygen, there was oxidation reduction involved there. That's beyond the scope of this class. And so you recognize that as being a combustion reaction, and combustion reactions are oxidation-reduction reactions. Reaction with elemental oxygen.
Does pure carbon burn well?
Pure carbon will burn, yes, it will. So, charcoal. How do they make charcoal? They take wood. I saw a documentary on this. They build these huts down in South America, and they chop down the rainforests, and they put all this wood into these huts, and they burn it. But it's in this hut that's clamped down and tight, so very little oxygen gets in there. And so the wood begins to burn, but it can't burn completely because it runs out of oxygen. And so why is charcoal black on the outside? That's carbon. And then you put that, and that's just going to burn, it's going to start burning a lot easier than if you just throw chunks of wood on your grill. And yet you also don't get all the ash and stuff flying off of it.
So
But
our briquettes are actually from deforestation.
Your briquettes, I don't believe are, but the real wood charcoal, and you kind of have to feel for these people because they make a living. They sell the charcoal and they make money to live on, but yeah, they're cutting down the rainforests. Gotta give them something else to do. Have you ever tried to chop down bamboo?
I thought they had to growing now, they can't chop down.
Well, there are regulations and stuff, but there are places where it doesn't matter what regulation there is, people are going to do what they need to do to survive, right? So it's kind of complicated. But this slide here is the things that you need to keep in the back of your mind about identifying redox. So a substance reacts with elemental oxygen, that was the last one. A metal reacts with a nonmetal, that was the first one. One substance transfers electrons to another, that was the second one. The third one had none of these things going on.
Can you go back for just a second?
Yep.
Get that down.
And these slides are posted on Blackboard as well. And the information is also generally in your textbook.
Okay.
Got it? So combustion reactions, this is still in section 7.9. Combustion reactions are a special subcategory of redox reactions. We just looked at something reacting with pure oxygen is a redox reaction. These are also called combustion reactions. So combustion reactions characterized by the reaction of a substance with molecular oxygen, elemental oxygen, to form one or more oxygen-containing compounds, and often water is one of those compounds. And so that might seem a little funny. You mean when I burn stuff, I'm forming water, and yet I use water to put out a flame? Yes, well, yeah, but you're generating small amounts of water, and when you're burning something, it's hot, and so you're giving off water vapor, and so it's not a liquid water that's going to put out your fire. Combustion reactions are exothermic. I think we generally recognize that. When you burn something, it gets hot, and it gives off heat. That's generally why we do that. If you have compounds containing carbon and hydrogen, or carbon, hydrogen, and oxygen, they always form carbon dioxide and water when you burn them. So pure methane, CH4, the products are carbon dioxide and water. Pure butane, pure octane. Any hydrocarbon or, push the button, any compound containing just carbon, hydrogen, and oxygen is going to burn very cleanly and give water and carbon dioxide as products. And so, you talk about, well, a clean burning fuel. Well, that's something that doesn't have a lot of other contaminants in it. Now, if we could, purify all of the oil and stuff and get rid of the sulfur and the nitrogen and these other compounds, then we could cut way down on pollution. But the cost involved in purifying those compounds is just ridiculous, and so it's just not feasible. So here's an example. Write a balanced equation for the combustion of liquid pentane. It gives you the formula because there's no way you would know what that formula is at this point in your chemical career. So liquid pentane, C5H12, liquid, they told us. Combustion, what do you need for something to burn? You gotta have oxygen.
You need to, it's H, you only put H2. It's crazy.
Or H12.
Thank you.
It'd be a pretty crazy hydrocarbon.
Yeah, that would be a crazy hydrocarbon.
So element to oxygen is the same thing as diatomic oxygen?
Yeah, oxygen as an element, because it's a diatomic element, it's always going to be O2. And this is one of the situations where it's important to recognize that. So when we have combustion of something containing carbon and hydrogen, or carbon, hydrogen, and oxygen, we're going to get carbon dioxide and water. What's the state of carbon dioxide? It's a gas. Now, water, you might say, well, that's a liquid. Okay, let's think about this. We're burning something. Is this at room temperature? No, this is above room temperature. The water's going to be a gas too. I wouldn't get on you about that, and hopefully Master in Chemistry won't either. So there we have it. They gave us the formula for the reactant, and then we know to put in oxygen, and the products are CO2 and H2O. Do you have a question? Okay, so we need to balance this. We have 5 carbons on the left. We'll put a 5 over here. 5 carbons on the right. And leave the oxygen for last. 12 hydrogens on the left. So we'll put a 6 in here. And we'll get 12 hydrogens on the right. And now let's look at oxygens. Over here we have 10 here. And 6 there, which is 16. So we need an 8 over here. And that's our balanced chemical equation. These combustion reactions are where we often get into an odd-even problem. We didn't in this one, but
If there's an odd number of,
I think it's if there's an even number of carbons, then we'll end up with a problem.
and you just double everything, right?
Yeah, if you end up with an odd-even problem where you need an odd number of oxygens, but they only come in pairs, then you double all the coefficients, and that magically turns your odd number into an even number. If only life were so simple.